So seems we are live since 5 seconds ago. Cool. So hello everyone. Let me first share the link through social networks. Hey, so give me a second. So I am live now. Cool. So this here now in Slack. Hey, live now. Let me know in the comments if you can see the live stream. So now that I'm done sharing, share now. Not now. Okay, share now. Yes. Let's go back here. Okay, cool. So since we're live, I'll just wait a couple of minutes. I'll probably just start right away as this is being recorded anyway. If you guys can't hear me, let me know. So today we are going to do 2 algorithms. I'm super excited about it because I've almost been rushing through the other sections just to get here in time. No, I'm kidding, but it's like I don't know. I feel like I'm not the type of person that likes to go through all the theory and all the maths and all this kind of stuff, and then kind of when I feel ready, I approach the algorithms. But the same we did last time with the exercises, that we start with the problems. Then that's kind of the way I like to do it, right? So let's start with I like to kind of go as quickly as possible to the practical stuff, to the algorithms, and then we will see if we've got trouble understanding some of these things. Then we might just come back to the actual maths and whatnot. We'll see. So we've got like a bunch of algorithms in here. I'm going to try to cover quantum teleportation and superdense coding, which are, by the way, these names don't sound hyped at all. I mean, when I first heard those names, I was like, that sounds cool, man. And I think they are closely related. I did them already. I went through a breakdown in my channel a while ago, but I haven't come back to them for a while. So I might actually get stuck a bit. We'll see. Let's see how this is explained in the guide, and let's try to code them. See how that looks like. So, and if we get stuck, we can always go back to some of these, single qubits and multi-qubit chapters and stuff like that. We'll see. So let's start with quantum teleportation. Good. This notebook demonstrates quantum teleportation. We first use Qiskit's built-in simulator to test our quantum circuit, and then we'll try it out in a real quantum computer. I will probably not do the real quantum computer thing because it's gonna anyway get queued somewhere and not give me any result. Okay, but I see this straight away code and some comment. Okay, so this seems to be the part where it's the actual IBM-Q. So the actual quantum computer. Yeah, you're gonna see this. Let me make that a little bit bigger. Some errors, I guess. This is, yeah, okay. So it doesn't seem a long chapter. Let's take a look at it. I can't see here. I see a lot of code, but I can't see any. Maybe there's the explanation of the algorithm. Okay, so yeah. Okay, let's go through this. The concept. The concept. So Alice wants to send quantum information to Bob. Specifically, suppose that she wants to send a state, so that kind of state where there's like it's in a superposition of a 0 and a 1, and this alpha and beta being the amplitudes of those amplitudes, phases, whatever, the proportion of zeros and ones that's in the state to Bob. This entails passing on information about alpha and beta to Bob. Kind of, yeah, I guess. So basically, we want to replicate that, but I know that I can't. I know there's this whole thing with the no cloning theorem that means you can't just copy things. But this hasn't been touched before, right? In the other chapters, I don't think so. I got new drawing tools. I'll see if those don't break the stream at least. Can I check the health? Yeah, that seems okay. Everything's fine. Cool. So there exists a theorem, okay, in quantum mechanics, which states that you cannot simply. And by the way, I'll try to give kind of 1 hour per algorithm. But we'll see. I mean, if we get done with that faster, then it's fine. If I see that I want to extend, maybe we go through a first hour and we haven't really taken anything interesting out of the first algorithm, then I might quickly switch to the other one and then see whether we have some spare time at the end to come back to this one. We'll see. But I want to give it sort of an even spare time. This is known as the no-cloning theory, exactly. As a result of this, we can see that Alice can't simply generate a copy of the state and give the copy to Bob. Copying a state is only possible with classical computation. However, by taking advantage of 2 classical bits and entanglement, Alice can transfer the state to Bob. We call this teleportation, as at the end Bob will have the state and Alice won't anymore. That's why it's called teleportation. So it's like you're destroying it on the one end. Let's see how this works in some detail. So how does this work? Okay, so it's a step-by-step explanation. Alice and Bob create an entangled pair of qubits, and each of them holds on to one of the 2 qubits in the pair. So this is going to be interesting because this is going to have to do with entanglement, and I haven't done a lot with entanglement. I haven't done a lot of reasoning with entanglement, and for me it comes down. I'm kind of exploring a lot the. I feel like I'm trying to grasp already. I'm starting to grasp already the interference concept a lot, and how can everything be boiled down to interference? But entanglement is still one of those quantum resources, or quantum things that I haven't really kind of gotten my hands dirty with. So the pair they create is a special pair called the Bell pair. In the quantum circuit, the way to create a Bell pair between 2 qubits is to first transfer one of them to the Bell bases, plus and minus, by using a Hadamard gate, and then to apply a C0 gate into the other qubit controlled by the in the Bell bases. Let's say Alice owns Q1 and Bob. So let me first, just in case, because I feel this is a bit, again, I don't know if entanglement has been, I haven't really, there hasn't been anything in here about entanglement. What's interesting about entanglement is how you kind of reason about it in terms of what's this correlation about. The way one way, let me open Quirk. One way to see these is when if you've got 2 qubits and you apply a Hadamard, and so it's kind of like and then you do that's what the text says, right? So that's how you create a Bell pair. For me, it helps me always to kind of reason about these as in, because entanglement really is correlation, as in like measurement correlation, right? So basically, if you're gonna measure a 0 up here, this will immediately guarantee that you're gonna measure a 0 on the other qubit, and you can see that independently they both have like a 50-50% chance of being on, but at the system level, that's the only 2 possibilities you can get. And one way to reason about this, and it's funny because I'm kind of thinking of this in a classical way, as in like a condition. If this is 1, then apply a control not. It's saying, so if I walk backwards, right? If let's try to use these new tools here. So if I walk backwards, what is this? Okay, exactly. If I walk backwards this way, oh man, I'm bad at that. You're probably seeing my hand. So if I move backwards this way, the first thing that I find is the control node. So it's like, if I'm trying to understand how I got to a certain measurement, if the qubit 0 is 1, then qubit 1 will be flipped, right? The problem is that this is not, this is either 0 or 1, so I don't know until I measure, because there's the Hadamard here, and that's what creates that entanglement, which basically means that measurements depend on each other. Like if I measure here, I will inevitably be able to reason about what's the measurement here, what was that qubit all along, sort of thing. So this is probably a really weird way of explaining it, but I think that helps me reason about it. I thought it was kind of obvious, but I don't think everyone thinks this way. I don't know why. It's just you kind of try to think from a measurement perspective. It's like, okay, so this is a conditional. So you're conditioning, you're relating those two qubits, but the value you're conditioning on is a value that is not clear until you're measuring. So that's why the correlation happens at the measurement level. So this is something that I still want to explore. I hope this is going to help me explore this algorithm concretely right now. That concept a bit more, because it's not that now, it's not that if I would now do something like that, I'm affecting the other qubit. I'm definitely affecting the overall state, but it's not that it's doing some kind of spooky action at a distance before the measurement, or at least that's my feeling. But that's a bit unclear. So I have to really explore this way more. Now, sorry for the tangent. Let's go back to the text. So, okay. Now, step 2, Alice applies a control NOT gate on Q1 controlled by, I'm so bad at the names. Is that phi? I guess so. The qubit she is trying to send to Bob. Okay, so applies the CNOT gate. Yeah. This is not explaining me why. It just says step 2, apply the CNOT. So that can be a bit confusing, I guess. Why is CNOT? We'll see. I'll try to put the circuit. We'll try to go. Okay, so here there's already some code, and we'll try to put the circuit together and try to reason about it. Step 3. Next, Alice applies a Hadamard gate to her qubit and applies a measurement to both qubits that she owns. Okay, Q1 and her original qubit. Then it's time for a phone call to Bob. She tells Bob the outcome of her 2-qubit measurement. Depending on what she says, Bob applies some gates to his qubit Q2. Then the gates to be applied based on what Alice says are the following. 0, 0, do nothing. 0, 1, apply a next gate. 1, 0, apply a Z gate. 1, 1, apply a ZX gate. That's okay. Note that this transfer. Okay, so this transfer of information is classical. The reason here is that the reason this is written here, I guess, is because I would be a bit confused. I know the reason this is written here is because for people to avoid saying, "Oh, that's faster than light communication." Now, all honestly, coming from a background like mine, like when I first read, I didn't even come to my mind, It's like I didn't even come to my mind that this could be, in theory, breaking some kind of laws of physics or whatnot. It's just then you kind of think about it. It's like, oh yeah, sure, of course, that would be super weird if you would be able to kind of transfer that information like faster than the speed of light. But yeah. And voila, at the end of this protocol, Alice's qubit has now teleported to Bob. Okay. But there isn't an explanation. There doesn't seem to be an explanation on why is this working. Right? Is a teleportation a real quantum computer? That's what I was interested in, to see how this would... Because I know, for example, in... is it in the references? I think I saw it in the references. Oh yeah, I saw in Nielsen's and Chang's book, there is a really neat explanation that is at the sort of mathematical level. You see how the state evolves, and then gate by gate, and then you kind of realize, and then you see at the end, if I remember well, like that it makes sense, that it kind of works, but it's still, I'm missing that here. So where was I? Let's go ahead. Maybe it's somewhere. Okay, so let's go ahead and build that. And then we'll try to break it down if it's not done. In this notebook, we will give Alice a secret state. This state will be generated by applying a series of unitary gates on a qubit that is initialized to the ground state. So go ahead and fill in the secret unitary that will be applied to 0. So I guess this is the... That's sorry. So I guess the reason for this is that this is probably the I think, what is this secret unitary? What is this? Where is this used? Apply secret unitary, simple function that applies a series of unitary gates from a given string. So that's gonna probably create the starting state from Alice, which is what we want to then transfer to Bob. I guess that's the point. Okay. Let's see. So if the quantum teleportation circuit works, then at the output of the protocol discussed above will be the same state passed on onto Alice. Then we can undo the applied secret unitary to yield a 0. So okay, so this way you check that it works. You kind of undo that, and then you check that you see the 0 you had. It comes up of a bit as of an awkward way to check that. Maybe it's because I'm spoiled with the way. Wasn't there? I think in Quirk there was a quantum teleportation. Yep, here. Okay. So this is the animation is cool though. So you can see here, this is the message, and I guess so what we're doing here is we're saying we apply, I don't know, a Hadamard and a Z, and that's the message, right? And so what you want to see here to understand and confirm that it's received is you want to apply a Z and a Hadamard, because then it comes back to 0, because you're basically undoing that. Okay, so I guess that's the deal here. Okay, we will then do a repeated measure. We will then do repeated measurements on Bob's qubit to see how many times it gives 0 and how many times it gives 1. Okay, so what do we expect? In the ideal case, and assuming our teleportation protocol works, we'll always measure 0 from Bob's qubit because we started off with 0. In a real quantum computer, errors in the gates will cause a small fraction of the results to be 1. We'll see how it looks like. Okay, so let's get started. What are we doing here? So we're now importing a bunch of stuff. Now this seems to be not consistent with the other chapters, isn't it? Because you're importing Qiskit as QK. It's not like I thought you were always. I mean, it seems like in the rest of the guide you're importing Qiskit just everything. There's probably a bunch of stuff we probably won't need if we don't do the actual run with a quantum computer. Okay, now we're defining the function. Let me check. Is it all going good here? Stream health is excellent. Cool. So it's telling me the audio stream's current bitrate is lower than the recommended bitrate. I recommend that you use an audio stream bitrate of, I don't know. Can you guys hear me well? I see there's a couple people watching. How about me? I'm hearable. Let me just quickly check on the sound here. Seems all good. So stream health is excellent. Okay, seems all fine. I was checking the audio, so because it's pretty cool. The YouTube the live control center gives you a lot of insights. Anyway, so we're now about to define this thing here, which is just for the sake of. So this is not really part of the algorithm. This is just for the sake of being able to prove that it works. And what is it doing? Let's take a look at it. So there's a map, and so it takes. Okay, so in theory, I don't have to apply the H and the Z. This is just a string, and then I can give it whatever I want. And it's going to apply the X gate, the Y gate, the Z gate, the H, and the T gate. And then if dagger, so if this is true, then it's going to apply the inverse, which for T is TDG. For the rest, is the inverse is their own, is the same gate. So that's why there's no change. And equals, wait a second, if dagger apply okay, so if it's dagger, you apply them in that order. If it's no, if it's dagger, you applied in the reverse order. Okay, yeah, because that's what you need to basically do when you uncompute, right? Okay, so I think we are now here, and so now we're about to start the actual circuit. Let's see. So what does it say here? So we create a quantum circuit. Qubit ordering as follows. Classical registers will just contain measured values of. Can I? I'll just read there. Wait, give me a second. So let me just take a look at this and see. I'm just gonna move my face, I think. Just I don't know where's the best place. Probably. I'm just gonna move my face over here. I hope that doesn't bother you guys, because I'm gonna be basically coding down there, so that's gonna make it easier for everyone to see the code down there. So so I copy that and I do this. And so what's going on here? So qubit ordering as follows. Classical registers will just contain measured values of the corresponding qubits. Q0, qubit to be teleported. Q1 is Alice's second qubit, and Q2 is Bob's qubit, which will be the destination. Okay, so apply the secret unitary to qubit 0. Then barrier, then Hadamard, control X, 1 and 2. I guess it's easy to read if I just draw it. In principle, if the teleportation work, okay, so this is just the comments in here. So if I, can I just draw it? So I will just do this and say QC dot draw output equals MPL, and we got the little circuit in here. Okay. The barriers seem to be there to make the drawing nicer, I think. So these Hadamard's don't kind of like get shifted around. Oh yeah, that's what I did. Okay, and then there's already the, okay. So that's it? Then we just go ahead, or what's the, so we do this and that is awkward. So we're getting the chasm simulator. We're doing it 1024 times. We're getting the results, and we're getting the counts, and we're plotting the histogram. And that's what we get. And how am I supposed to read these results? Now, I guess, okay, Bob's qubit is this qubit. It's always 0. Okay, I think that's what. Note that the results on the x-axis in the histogram above are ordered C2, C1, C0. Okay, yeah. So we can see that only results where C2 equals 0 appear, indicating that teleportation protocol has worked. And that's it. Teleportation on a real quantum computer. So I'm a bit confused because I would expect some sort of walk through the circuit. You know what I mean? Guess nobody's complaining, but I guess the audio is fine. So I would expect some sort of walk through the circuit, honestly, because that is not trivial. I mean, again, it's probably trivial for someone who, you know, is fluent in all this stuff, but you know, there's okay an entanglement in here. Why does this make it work? It's not obvious to me. This seemed to be rather something that you're correcting, kind of. You're saying, okay, so it seems like you're fine-tuning the final result based on the stuff you're measuring. You're saying, okay, so if I measure that, then I'll just tweak that a little bit and then add a control knot, and then, because it even seems like this Hadamard would be attempting to read maybe the phase or something like that, and then based on that, so if I measure a 1, let's assume that let's assume that I got like a sort of a 0 plus 1 state in here, right? And so, or a 0 minus state in here, exactly. And so when I go through the Hadamard, I'm gonna have a 1, so it's gonna read a 1. So what this is doing here, this control Z is basically taking that 1 and saying, okay, so I gotta encode that phase that I know it's a 1. I gotta encode it here, so I apply a Z down here. I don't know. That's maybe one way of saying that, but it's probably not correct. But you know, like I would expect some sort of walk through the circuit, which we can try to do now. I mean, we've got time. It's like, okay, so we just half an hour in. So we've got half an hour probably to try to walk through these and play with it. Because I also, one of the things that I think is really helpful is get the circuit, move gates around, see if you could build it anyhow else, and then try to understand why that particular configuration works. I think that's super helpful. But now I got to close that somehow. So yeah. So this is kind of missing in here, because then the second part is, okay. Okay, let's read that. What's the third measurement? Let's read that. So in IBM quantum computers, currently you do not support instructions after measurements, meaning that we cannot run the quantum teleportation in its current form on real hardware. Fortunately, this does not limit our ability to perform any computations due to the deferred measurement principle. What's the deferred measurement principle? Reference number 1. Well, yeah, I guess that's that's one of those cases. Like, I think someone said that in the last session or in the first session, I don't know, that the references kind of suck in the sense that they're referencing a book that you need to buy. I mean, it's not available for free legally, I guess. And I got a copy of the book, but I'm not gonna. I mean, it doesn't even tell me where I can go look for these. That sucks, because I mean, I'd like to know what the deferred measurement is, what the deferred measurement principle is. Let's see what Wikipedia says. So the deferred measurement principle is a result in quantum computing which states that delaying measurements until the end of a quantum computation doesn't affect the probability distribution of the outcomes. Cool. Okay. That's easy. I mean, easy to understand. I mean, I'm not saying it's easy to prove, but two equivalent quantum logic circuits, one where the measurement happens first and one where the operation conditioned on the to be measured qubit happens first. So it's a controlled unitary and then we measure. Because I guess the point here is that when you measure that, you're kind of collapsing part of the state, and it's kind of, it doesn't matter when you collapse it, right? You can collapse it before the controlled unitary, and then, like, let me try to, because I think Quirk has really good tools for that. It's called post selection. So let me clear these. So if we've got a, let's say a, let's use a control X as an example. I don't know if it's going to be good, right? But we've got these. So basically, let's use the entangle like a bell state, right? So it doesn't matter. So what this is telling me is it doesn't matter whether we are measuring here, right? Look at this. Let me zoom in. Assuming measurement deferred. Okay, so this is it. Basically, is telling that those amplitudes assume you haven't measured yet. I guess that's what it's telling me. So it doesn't matter whether you measure here or you measure here, right? And I think you can. One thing you can do that. One thing the one where you can see that in the simulator here would be to use post selection. So what post selection does is it's assuming that you've measured something and then trashes everything else, right? So it's saying, okay, let's assume, so if I post select for 0, what this is doing is assuming that from that point on, everything else that's not a 0 is just off the table. It's not there. It's you know, trashed. And sorry, everything that's not 0. So it just keeps the zeros, right? Which basically it collapses that as well. Like it's I don't know if collapsing is the right word, but you can see the block sphere here. It's 0, right? Because now we know we've measured, like it's almost like you're simulating a measurement in the sense that you're saying, okay, let's assume we just keep the zeros. What happens to the other state from that point in time? Well, it's a 0. If I pause select with 1, right, now we're keeping the 1s. So this state is not anymore like, you see now it's entangled, right? So, but it's not anymore once you pause select. So now it's 1 because yeah, you're forcing this to be 1. And I guess what this is saying is it doesn't matter where you do the pause select, right? So here it works. Sorry, so this works. Okay, because it's almost like it doesn't matter, right? Like if you're saying no, I'm gonna keep the ones in here, like that control is gonna behave the same. Now I don't. This is not so obvious that it works like that for all possible states to me. I mean, I wouldn't just be able to say, yeah, that's how it looks like, that's how it works, all good. But let me see a second here. It keeps warning me about the audio, but as nobody is complaining, I hope the audio is going to be fine at the end. If not, it's a pity for the recording. But it's a suggestion, so I'm not. I don't think this is like necessarily extremely bad. It's like there's always something bad. What does it say here? Okay, we'll see how this looks like at the end. Now, yeah. So that's the point, right? So it doesn't matter where you're measuring. In this particular case, it's not, the collapsing happens anyway. Whether you do before the control or after the control. So that's what this is. So that's what this means, is that in the real hardware you can't do this. You can't have the controls after the measurement. At least not in IBM's hardware. But what this is saying is you can, by means of this theorem, you can just move those measurements at the end, and then you should kind of get the same result. I mean, we even can try here, right? In the simulator, I mean. So what if so we move these measurements at the very end. We apply this, we draw the circuit, and now you've got, okay, not here, let me see. At the very end, like let's do this really at the very end. So at the very end here, we draw the circuit, and now the circuit is like this. Oh, come on. Why is the Z getting drawn like that? Anyway, the result hasn't changed fundamentally. So it's like you still see 0, 0, 0 as the C2, as the classical B2, which is what kind of matters. Okay. Back. Why doesn't this snap together? Again, some sort of. I might think. Oh, thanks. Thanks, Sam. I guess that's you with the audio. Yeah. Thanks for confirming that. So I don't know if. Okay. So where was I? Deferred measurement. The principle states that any measurement can be postponed until the end of the circuit. Yeah, any benefits of measuring early are hardware related. If we can measure early, we may we may be able to reuse qubits or reduce the amount of time our qubits are in the fragile superposition. In this example, the early measurement in quantum teleportation would have allowed us to transmit a qubit state without a direct quantum communication channel. Okay, meaning that okay, yeah, I get it. So what it means is that, I mean, the whole purpose of moving the measurements at the end, moving the measurements at the end, it kind of removes the purpose of the whole interpretation, because it's sort of you can't classically communicate, right? You can't tell, Alice can't tell Bob, hey, I measured that, so therefore apply these operations. And so it's not really teleportation, because you're kind of connecting these two qubits, right? You're doing a control operation on a qubit that it's still like it's still in use. So that's not anymore, you know. That can let's put it this way: that can't happen because essentially Bob's qubit is maybe, you know, like 100 kilometers away, right? So you just can't do that. But I guess that's the whole thing here. Is the whole point is the results should be the same. While moving the gates allows this repetition, however, it should be noted that some of the benefits of the repetition process are is lost. So okay, so we've got the same thing in here. Okay, same thing in here. Executing, you will now see the results of the teleportation algorithm on a real quantum computer. Okay, yeah. So essentially, what this is telling us that there is indeed a portion of the results that have C2 equals 1, and those shouldn't happen. But this is because of the errors. The experimental error rate, the error rate percent is okay. The sum of okay, yeah. So they calculate the errors. It's 11%, and that's it. Okay, so there's no real walk through the circuit. I think that's from a feedback perspective, like a big minus in here. Like if I'd been new to this, I was like, yeah, that's just a recipe. That doesn't tell me why it works. It doesn't walk me through the circuit. I mean, I get it. You can always go and turn the circuit into math and then see how this is evolving and see that it's working. But it still feels like there's a lack of a walkthrough, which we may try to do now. So how do we want to approach this? Let me do the following. I think we're done with this for now with the Jupyter notebook, so I'll just do that here. Let's take a look at Quirk, because it's going to make it easier for me to just move things up and down rather than just playing with the code, I guess, and redrawing and whatnot. That just let's take a look at what can we do next. So we've got, okay, so let's spend the next 20 minutes on Quirk's implementation, and then we'll move to the how's the other called? A superdense coding. Yeah. So here there is, if I clear this and refresh, there is quantum teleportation. So there's a bunch of example circuits, which this comes in really in handy. And now Quirk does some funky things here with animations, which we can I guess get rid of, because I mean, you can see the two block spheres are identical. That's kind of the point here. It's proving that you're moving that single state from here down here, and I guess these two qubits in here are just used to kind of see, like, express that, you know, this qubit can be really far away. So, but I think for the sake of analysis, it's going to be better if we get rid of the message. Again, this is not working really well. Yep. And okay, now it's stopped moving, and then I can get rid of those wires in here, which were just for illustration purposes. And now we've got the this is also just like the nothing gate, I guess, like the spacer. Okay, the gate has no effect. It's just to illustrate that. It's just to illustrate that the the entanglement happens before. That's kind of the input of the algorithm is a pre-entangled pair of qubits. Um, Now, how does this? What's a way to reason about this? How can we even start? I mean, there's here absolutely nothing about it. One thing that I had in mind was okay, like that there is something that seems like a correction being applied here. So I was thinking maybe there is some sort of entanglement between so you're maybe somehow correlating. That's a theory. I'm just theorizing right now. I'm just like playing with it with a couple of ideas. Let me move this toolbox down here. So you're just this. Okay, let me clean up. So you're taking this qubit in here. You're correlating it somehow with the pair, as in you're correlating the X measurements, right? Because now you're going to measure these, and based on this measurement, you're going to apply some sort of correction down here. And I think I should buy some sort of pen, like a real, actual real pen. Would be much nicer, I guess. And these, and then here you're using basically a Hadamard gate to then maybe try to read out the phase and then apply a correction based on that. That's a guess, but I'm not so sure how could I arrive to that. It kind of seems to make sense in the sense that there are two things you need to transfer, right? We talked about here they talk about transfer alpha and beta, right? The reality is alpha and beta are the amplitude. No, okay, they're not the amplitudes, but alpha and beta is part of the information because there's amplitude in there, but there's also phase in there. Which in this case, there's a plus in here, but there's some relative phase in the one component that's even part of beta, so to say, that needs to be transferred as well. So that would be one way to look at it, maybe. But what we can take a look at is we can take a look at the amplitudes and see what's going on here at the system level. First of all, let's pick up an initial state that kind of makes sense. For example, the minus state, right? Minus state. So if I now take a look at the amplitudes in here, what have we got? So we've got it seems like this is kind of, you see, that's the minus state, and it appears duplicated here and here right after entanglement. So the interesting part in here is already that, I mean, this is because of we're taking a look at the system overall, and so we're having, so here you've got the first the two qubits starting from the left, 0, 0, 0, 0, right? So this is both 0, 0, 0, 0, and here's 1, 1, 1, 1. And so you've got, it seems like that stayed related to this and to this. And I guess the idea here is, if you would like to take a look at these from a mathematical perspective, maybe you could think of these as being, and now I hope this is not gonna break anyhow. So it's almost like if you would have, so you've got your state which is 0, 0 plus 1, 1, and I'm omitting here the normalization and all this kind of stuff. It just makes notation simpler. And you're having like a, this is sort of a product with your minus state, right? Oh, I missed the brackets there and stuff like that. And so this is something you kind of, you would multiply like that, right? So that literally is telling you that you've got a 0, 0 minus and a 1, 1 minus. And that's kind of what this is doing here. Okay. Um, now, if I so after the control node, what's happening? Okay? What does it look like here? So we're moving these two things. We're moving them here. So now it seems like that's really confusing. Okay. Because I can see where this is going, as in like after the Hadamard, we've got basically a superposition that it actually, what we've done is, if you pay attention, this state here, it's been kind of like flipped from row to column, and now it's here, right? No, that's not it. It's actually here and here, here and here. What am I looking at? So let's use pos. Let's say we pos select for 0, 0. Okay, so we pos select for 0. But you see, okay, so that whole thing goes away. We pos select. Okay, so those are the states we're looking at. We're looking at these and these. So yeah, these and these. So you see. Okay, so if we pos select for 0 and 1, we've got this state, but this state needs to be corrected, right? Because basically the relative phases are flipped. So we're saying that the relative phase of 180 degrees here is in the 0 component, but it should be on the other. So you apply a control node. Okay, so that's where the correction comes. So effectively, it seems what we're doing in here is we're trying to move. It feels like we're trying to move the state within our superposition. We're trying to reorganize or create a superposition that will basically collapse as we destroy these. As we collapse and read those qubits, it's going to collapse into. So you've got different possibilities. Okay, so let's try to paint them. I can't find some drawing tools that work nice, that don't break my my performance in here, or I just have a stupid machine. That's another. So these, I'm gonna try to be careful with these. These and these is one of the possible things you will read out. If I change now to this color, the same is gonna be these and these. But this is gonna need a phase correction because they're both. There's no relative phase in here, and these. Okay, and then here you've got these and these, which I think they just need. Yeah, those are the ones that they just need a control node, I think. And I'm gonna pink or lila. I don't know what this is. And now we've got this here and this here. So those are the 4 possible outcomes, depending on how your measurements are going to look like. And I think that kind of relates. To these in here. Okay, that kind of makes sense. But how you even come up with this? I mean, come on. How would you design that algorithm? That's what I'm trying to understand, right? I'm trying to understand. It's not just a walkthrough. I mean, now I can see how this works. So you're rearranging the superposition so that you get that. And so one question here would be: would we be able to build that without entanglement? Maybe let's. Okay, so it's like 5 minutes to 10. Let me just give it a couple of other thoughts, and we'll just stop it here, then go to quantum to super dense coding, and then we'll see how we spend the rest of the time. Because I think it's a nice exercise to do that, but it takes time. Definitely takes time. Just to play with stuff, it just takes time. It's not so intuitive. But you see, each of those possible measurements need a correction. So they actually then resemble, or they actually are the same as the state up here. Those corrections are sort of a natural effect of the Hadamard, I guess, and that Hadamard as well, and the entanglement. So, could we do this? Let me try quickly to try to do this without. Let's try to do this without entanglement. I know it's not the purpose, but let's see if we could do something like that without entanglement. So let's assume there's no entanglement. So we get rid of these, we get rid of these. But I guess we want to get to the point where we are able to here kind of read out the same thing. So we need. My first guess would be if we just have Hadamard, that's kind of giving us some. Okay, so it's not the same what we're getting with entanglement, but it's pretty similar. Now so if I apply another Hadamard in here, right? Now the problem we're going to have is that we can't distinguish once we measure, once we collapse and we postulate, we can't distinguish what are the corrections that we need to do. But if you would do it this way, and then we would postulate and postulate for 1. Now what's the block sphere down here? So that now you would only need to apply a phase correction here. And we're done. If we postulate for 0 and 0, we need to do nothing. If we postulate for 0 and 1, 0 and 1, then we also need to have a control Z. I don't know. I don't know if it makes sense what I'm doing, but and if we postulate for 1, 1, you need to mess up with this now. You need to do some extra correction in here. Maybe partial Z rotations. I mean, I could always say, I could always do that. And if I now, that's not needed. If I now add a little animation in here, but that's not working. That's not moving at all. So I basically have just yeah, that's absolutely nonsense. Why it doesn't work for the other states? So for example, why it doesn't work for -I? All I'm trying to say is, all I'm trying to figure out is what is the entanglement contributing to the whole thing, right? Because once we've got these, if we now post-select amplitudes, because I think people give it for granted that. So wait a second. So now, if we now post-select, now we're gonna measure 1 1. So this is gonna, yeah, okay, that doesn't work because those corrections here are not, you can't just do those corrections. Yeah, so that's not working for these cases. What is it in the entanglement that makes it work? That's my point. Let me try to get rid of all these. And I'm just exploring here, so we'll move into the next algorithm in like about 5-10 minutes. Okay, so what's in the entanglement that makes it work? Is the fact that, because if we just have a Hadamard here, if we've got that, so this is the fact that it kind of creates that, it allows us to create that superposition that is basically mirrored. Like, if you take a look at these amplitudes and the phases, sorry, not the phases of, so this would be 0 0 0 0. So this is for the case 0 0, where the two first qubits are 0 0. These are the same in here. And when it's 0 1, 0 1 and 0 1, they are mirrored, and 0 0 they're mirrored. Somehow that there is a relation with the phases in here, right? But that's just, it's like I kind of see how it works, but I'm not so clear on the why it works. Let's put it this way. Because I like the interpretation of, so one of the things I try to find interpretations that are kind of a bit out of the box, or maybe a bit out of the mathematical box. Because all you can see here is the same like you can see with the math explanation that's in Nielsen's book, which is just you're moving stuff around in a way that then you can collapse that, and then you get just different versions of that state, and then you just apply certain corrections, and so you can distinguish. So each of the different measurements you've got like are distinguishable in the sense that you can uniquely correct them. But I'm more interested in understanding what's the nature of entanglement in here, and then why that, like whether it's sort of a higher level interpretation. But that's tricky. That's something tricky to do, especially with the time given. So, but I probably should do a video on that, because it feels like, as I said, it feels like this Hadamard in here could be understood as you're trying to read the phase, right? So let's give an example. So if we've got I mean, I think I've done that already. If you've got a minus in here, right? When you're going to read that, you're going to have a 1. You're going to see a 1. So what you want to do down here is you want to correct that phase by applying a Z. Now, what happens if I have a funny thing like? What if I have a funny thing like, say, instead of a superposition like that, like, I don't know, let's have a quarter of a quarter rotation of an X. So now this has a, does this have an minus 90 degrees? And yeah, and this is, is that correct? That's all awkward. 90 degrees. If you've got a block sphere in here, that's halfway. If you put a fourth, the amplitude's okay, but the phase that's added is the same. It's a 90 degrees phase. Okay, yeah, but the amplitudes are slightly different. So here the amplitudes are 50-50, and here the amplitudes are not 50-50, but they're like, you've got 85% and you've got here 14%. Okay. So if that's the state, what's going on here? So the phase is still 90 degrees. So the relative phase is 90 degrees. So when you're going to apply the Hadamard in here, you blocks of the local state. I cannot know it's the relative phase though. And if I take a look at the amplitudes of just that, it's probably going to be be messily entangled. Yes. But basically, there is a relative phase of still, like, because the relative phase is still minus 90 in here, right? Is it? I think so. If we pause select for 0, then what do we have in here? If we pause select for 1, well, what am I doing? What is left in here? If we pause select for 0, something's not. I'm either missing something, but this seems to be something worth exploring. As in, like, it feels. Oh, sorry, I lost the Hadamard. So it feels like that Hadamard in here is telling me something about the phase, right? Yeah, because you're basically going. It's almost like if you were doing an X measurement, right? Now, how do the amplitudes though get anyhow correlated? So you are this must have something to do with this control X in here, but also this one in here, sort of both control X's, I would say. Let me just quickly check. Health-wise, all good. That's perfect. So, what time is it? Okay, it's 10:02. Let me just give me 5 more minutes, and then we'll move to the other one. Then we'll probably come back, because that's definitely interesting. Something to take a look at. What if I would say that, maybe let me first clean up this, because I got lost already with so many things. Good, so we got these, we removed the message, the animation, we removed the wires. Good, so what is this essentially doing? Let's go back to the quarter state in here and then take a look at the amplitudes. And that's the block sphere kind of thing. Sorry, I should probably put all these in here so it's nicely separated from the entanglement. So but this is just 2 different views. So you want to get that 90 degrees correction down here as well, right? And the amplitudes as well. So let's for a second ignore the block spheres because they're just confusing me. So that's that phase. So what is the control knot doing in here? Up to this point, this is entangled. So you can't just take a look at that subsystem. You have to take a look at the whole system in here. So this is entangled. So when I do this, what's going on? It's some sort of entanglement as well, right? Because this is unclear. Like it's not, you know, it could be a 0 or a 1. And so the maybe a way to see this is that because now this proportion of amplitudes in here has been spread out, right? If you see here it's 85% roughly, so and it got split out in the zero component. Like the rightmost qubit is 0 here, but now we've got 42% and 42%, which is then roughly this 85%, and then here you've got that 14% spread across like 7%, 7%. So you are, so this is some sort of yeah, you're kind of entangling those amplitudes, and I'm probably using an awful language in here, but it seems like this way. So you're entangling the amplitude somehow, and then yeah, because if now you were to measure, let's see if we could just, for example, ignore, let's say we're not aiming at teleporting the phase information, we're just aiming at teleporting the amplitude information. Maybe that's a good exercise. So we don't care about the Hadamard in here. So if we get rid of the Hadamard and we get rid of these in here, we're done. Huh. Because we've collapsed now these, so we are post-select, we're measuring here, and so if we're post-selecting, but this measurement needs to happen. No, it doesn't need to happen. Bam. You just, I mean, I don't know, okay? I truly don't know. But I could try with Qiskit. We could try to do this with Qiskit. This confuses me a little bit. But anyway, let's maybe take a break for a second. Let's just go to the other algorithm. And then let's go back to this, or not. I'm confused because I feel like I'm into something here. Yeah, but in Qiskit I won't be able to take a look at that subsystem. I don't know how to do that. But it seems like it's kind of working. As in, like, if I measure here, it means I'm gonna either keep these and these, because they're both 0, or I'm gonna keep these or these. This means if I pause-select for 0 here, that's the ones I keep, right? If I pause-select for 1, those are the ones I keep. And pay attention that the amplitudes kind of stay. So so we've kind of entangled the amplitudes to some extent, yeah. If that's something you can say. Now, and you don't even need to, no, you need to correct, because if you do a pause selection in 1, you basically have the we're now taking just a look at the so the one component has the 85% of the amplitude, but it should be the 0, and yeah, so you need to correct that, and that's because of the effect of the Hadamard, I guess. So but that's one point, yeah. And so you could, and now the thing is, when you want to now basically teleport the phase information, what you want to do is you want to apply a Hadamard, right? But now that's gonna kind of create that superposition. That's the tricky. That's that's where I get lost a little bit, right? But if you apply a Hadamard in here, I can't still take a look at that. I can't take. This is all entangled stuff, so I can't take a look at the phases in here. But essentially, how can this tell me what's the correction that needs to be applied? That's the point is, I'm assuming that you don't need to just tweak the phase with high precision, because all what you're doing with this control X is, the relative phase remains the same. It's 90 degrees. It's just that the same way you gotta correct on the amplitudes, you're going to have to correct based on what you're measuring in here. So you're going to have to, because then your 90 degrees will just become 180 degrees. No, minus plus 90 degrees, and then you just got to flip the thing. So I think this is where it's going. I don't know. I think I should definitely do another separate video on these and try to find an intuitive way of explaining quantum teleportation, that it's not just going through the math or just going through the amplitudes and phases and seeing that it just works. But my point, I'm missing a walkthrough. I'm really missing a walkthrough here. So, because I think that helps you a lot. Maybe it's on purpose. Maybe just, okay, try to put the reader into my situation right now. Try to walk through these, and you can, I think, learn a lot if you do it this way. So let's move to okay, we're like, it's 10:10. Let's move to the next algorithm, which is superdense coding. And so it's loading, and we'll just do this and then probably save that. So this is going to be teleportation, and we're going to open up a new notebook. That's so slow. New notebook. I don't know if this is my broadcasting software, maybe, plus computer. We'll see. Okay, so superdense coding. Drink some water. This notebook demonstrates superdense coding in quantum computing. We first use Qiskit simulator to test out the quantum circuit, and then try it out on a real quantum computer. So I guess I'm going to do the same. So this is going to be... So there is the process explanation, there is a simulation, and then I guess there is a real quantum computer thing, which shows you that there's some kind of error. And I guess that we can probably skip that. I mean, it's interesting to see maybe the accuracy of these algorithms. 93%. I think in quantum teleportation there was an error of like 10 or 11%, so that seems to be better. But let's see. So the difference between superdense coding and quantum teleportation. There's also superdense coding in here, so, but I'll just what I will do is I'll maybe open it in a separate. So I'll open it in a separate thing, and then do superdense coding. Nice. Okay. So quantum teleportation and superdense coding are closely related and might cause confusion if not properly explained or differentiated. Quantum teleportation is a process by which the state of a qubit can be transmitted from one location to another with the help of a classical communication and a bell pair. In other words, we can say it is a protocol that destroys the quantum state of a qubit in one location and recreates it on a qubit at a distant location. You see, that recreation is what it's kind of nice to see this to see it this way, as in, like, it's what I was saying by talking about those things being corrections, right? Those measurements in here being corrections. It's kind of recreating the state, but it's destroying it, sadly, because when you want to measure when you want to apply the Hadamard, you're kind of destroying that, and then when you're measuring so that you know how to recreate it, you're destroying. That's the point. So superdense coding is a procedure that allows someone to send two classical bits to another party using just a single qubit of communication. If I remember well, I think this goes along so this is using the strategy of using amplitudes, or using the x and the z, or using two other dimensions to encode data, and then so you can then decode it if you know how to, and then you know what your 2 qubits are. The teleportation protocol is actually a flipped version of the superdense coding, in the sense that Alice and Bob merely swap their equipment. Okay. I don't know what that means though. Third party encodes qubits. Send 1 qubit to Alice, 1 qubit to Bob. Alice encodes a message. She sends the qubit to Bob. Okay. So Bob needs access to the. Okay. But look at this. It's using the same. Okay, so it's using the same trick. It's using this control node and this Hadamard gate. So this is the. That's why they're really related. Okay. It almost seems like it's the same, but there's no third, like it's just 2 qubits. There's no channel in between. I don't know. So step 1. The process starts with a third party who we'll call Eve. 2 qubits are prepared by Eve in entangled state. She initially starts the 2 qubit. By the way, it's a bit awkward you're calling it Eve. Isn't that Eve because of eavesdropping? I think that's where the whole Alice, Bob, and Eve thing comes from. It's like when you're doing some security analysis and you're going through different path analysis, and Alice and Bob are 2 people trying to share stuff, and then Eve is trying to eavesdrop. So the fact that Eve is it's just a fun thing. I just came up. The fact that Eve is preparing the entangled state seems a bit suspicious. Would you trust that entangled state? I don't know. Anyway, that's a bad joke. Yeah. So she applies a Hadamard gate. She initially starts the 2 qubits in the basis state 0. She applies Hadamard gate H to the first qubit to create the superposition. Then she applies a C0 gate. That's how you create the bell state, the bell pair. Okay. If first outcome states if first applied Hadamard gate. Okay, so there is a bit of a walkthrough here. That's nice. So you've got 0 and plus, and then you do a control node, and then you have 0, 0, 1, 1. So that's the bell pair. Okay, cool. Step 2: if sends, I guess, the first qubit to Alice and second qubit to Bob. The goal of the protocol is for Alice to send 2 classical bits of information to Bob using only her qubit. But before she does, she needs to apply a set of conjugates to her qubit depending on the 2 qubit of information she wants to send. I wouldn't say that this is something that she must do before. That's the actual encoding, right? That's what I'm kind of... Okay, the gates you're going to apply are going to be related to the message you want to send. Okay, encoding rules for superdense coding. This is Alice's protocol. But is this protocol public? I guess. It's like everyone knows this protocol. Or can you just come up with whatever protocol? This if she wants to send a 0, 0. Wait a second. Coding rules for this. Okay, so this if she wants to send 0, 0, she has nothing to her qubit, the identity gate. If she sends 0, 1, then she applies the X gate to her qubit. Okay, so we have only 1 qubit in here. Depending on what she wants to send, she applies the appropriate gate. Alice. Okay, then she wants to send. She applies the appropriate gate. Alice then sends her qubit to Bob for the final step in the process. So there seems to be some rendering issues in here. That's step 3, okay. Step 3. Bob receives Alice's qubit and uses his qubit to decode Eve's message. Notice that he does not need to have knowledge of the state in order to decode it. Yeah, but what about the protocol? Does he need to know the protocol? He only needs knowledge of the restoration operation. Bob applies the C0 gate using the first qubit as control and the second as target. Then he applies a Hadamard gate and finally performs a measurement in both qubits to extract the classical bits encoded in Alice's qubit. When Bob performs the measurements, he ends up with 4 possible outcomes with probability 1 each. Okay. This means there's no, you end up just with that probability. So note that the last outcome has a negative sign. Minus. Running it as 1-1 is also correct because the probability is calculated as the amplitude of squared. Okay. Simulating the superdense coding protocol. Yeah, but again, it doesn't seem like there is an actual walkthrough on why this works. So that would be, again, my feedback here. Okay, but this seems a fairly simple circuit. Let's go ahead and do that. So I just copied the imports that are necessary. And now we take a look at the circuit. But that's, again, so this is just what we read, right? So generate the entangled pair. Then Alice applies her message. So here we apply. So here we're sending 1-1. That's what I assume, right? Because we're applying a Z and an X. Shouldn't that be the opposite? Like, isn't the how's it called, the convention that the rightmost is the gate is the one that you apply first, and that's what you apply second. So here it's like this. Maybe that's just a typo in here, I don't know. Alice sends her qubit to Bob. After receiving qubit 0, Bob applies the recovery protocol. So how much this recovery protocol depends on the encoding protocol. Again, this okay. So let's put it this way: this is nothing to do with security actually. So I don't know why am I even making these comments. It's just encode 2 qubits in one, encode 2 classical bits in 1 qubit, and then decode it. So if I do that, that's the circuit. So entanglement, then encoding, and then decoding. Okay. She does not. Okay, so we're done, and then that's it, right? I mean, now we can now simulate. Okay, that's what I did. And now you simulate it, so we get the backends and all this stuff. And we plot the histogram, and we see that we get 1-1 with probability 1. So now let me play with this a little bit. So if we change these, and what happens if I change the order? Does this work still? QC Z 0. So does this still work? I do like that. And then I do like that. That still works. So the order doesn't matter. XZ, XZ, and ZX shouldn't really matter here. I see. Okay, but if I apply just an X gate, for example, I'm gonna comment that out. Then we got basically 1-0. Okay, something's not right here. I just applied an X gate. Oh yeah, no, 0-1. So I should get 0-1, and I get 1-0. So again, I don't know if this is a again convention-related thing, because if I apply the Z gate, then it's 0-1 and should be 1-0. Okay, can be a bit confusing. So that's maybe one feedback point in here. And if I don't apply anything, then I should get 0-0. So that is that it works, yeah. Okay, but it's still there's no. Yeah, well, that works because it's basically uncomputing. So it's So the decoding is the decoding protocol is literally unentangling. Okay, that's interesting. That's an interesting insight. I'm not going to go through, okay, so the simulation is done. I'm not going to go through the real quantum computer, but it's just the same, just with a real machine, which I believe this is a real machine, so it's all good. But let me, sorry, I hope I didn't leave you deaf now with my coughing. And let's see, so let's try to play with this in Quirk, because it's going to be easier to drag and drop than to just play with the code here, I guess. And so that's not what I want. I want these. Okay, let's simplify that a little bit. Again, some fancy animations in here. Get rid of them. So the way Quirk does it is, that's pretty cool. Okay, so you're you're encoding here, just so you understand what this mess is here. So these are your input. These are your input qubits, and then it turns them into classical qubits, and then applies the encoding protocol. That's a nice way of putting it here. So it's also an X or a Z. It's just they are controlled on classical qubits. Okay. Oh come on! Why does these things appear here? Now it simulates the send with a swap. That's nice. But I think I'm gonna get rid of this just to simplify the analysis. So here's an entanglement. Then then the qubit is sent by swapping, and then this readout, the decoding happens down here. Okay, let's try to simplify that. First of all, I'm gonna get rid of these, and I'm gonna get rid of these, and I'm gonna move these things in here. So I'm gonna actually do the swap like physically by I'm trying to get rid of the wire. So, and I'm gonna get rid of this wire. Okay, so now we have that's gonna be easier to analyze, I guess. And yeah, so here we see off. So if I turn the one in here, bam, that one turns on in here. If I turn the one on here, then turns on in here. Yeah. But it does seem okay. Let's first thing I want to try. That's the order matter. So whether we do first these or then these. So if I have 0, 1, then we get, so I have 1, 0, then we get 1, 0, 0, 0, 0, 0, 0, 1. Well, seems like it doesn't matter. So I guess that's not a problem in here. It's just not consistent with the way the code is written. So that might confuse some people right away. Okay, now we got now, okay, so we've got an entanglement in here. So, and that's actually interesting because I think it can help me understand the teleportation better, because now I realize that this decoding is literally the inverse of the Bell state creation. It's sort of unentangling. So let's take a look. So this is your entangled state. So what you're doing is you're basically using the fact that that there are like four possibilities that you can build out of a Bell state if you kind of combine the operations of like the Z, so the phase flip and the beat flip, because you can basically create so you can basically create, so you've got 0, 0 plus 1, 1. You can just flip, you can flip the sign and then have 0, 0 minus 1, 1. So that already allows you to encode like a binary value, right? Like, because you can then apply. So let's deconstruct that a bit. If you don't, let's say you just want to send one bit of information in one qubit, which is stupid, right? But let's say you want to do it this way. So you can still do it by saying we're not gonna apply these operations. I'm gonna get rid of these. And so now what this is doing is, and actually I think you don't even need that. No, you need that. Do you? I mean, you don't need that. Yeah, you don't need entangled state, literally. If this is a 0, then it's a 0. If it's a 1, it's a 1. You see, it's just that bit of information is transferred, because what you're doing is you're taking a state and just flipping the phase. Okay, that's not the 0011, so the 001 is the 0001, so it's not the bell state, but again, the difference, you're just encoding that into a Z, like a flip. So when you uncompute that, then you are going to be able to basically read out that state. So that's the deal here. And so let me rebuild that. And so with a now it's again. Okay. Now I think I'm back at the right algorithm. Yeah. So now the trick here is, how do you encode the second bit, a classical bit of information? So what I'm guessing is that you've already used. So see if you could use like a control Y, or that wouldn't work. I think that wouldn't work, because basically the Y and the Z, but they are still orthogonal to each other, I think. So that could be an interesting. No, you can't, I think, because they would just be biting off each other. They would just be messing up with each other, I think. Because you've got, I mean, you've got three observables, right? So you've got X, Y, and Z. So maybe an interesting exercise is, why cannot you encode 3 classical qubits of information using 1 qubit? That could be an interesting exercise to do as well, which I might try to do. It's an interesting idea. I think there is, I don't know if I have, I feel like I've gone through this before. I think that Craig in his AlgaCert, so I think AlgaCert blog, he talks about, I think, superdense coding, superdense coding, so encoding or 3 qubits. There was some blog post where he was trying to, I think it was exactly that exercise, trying to code 3 classical beats into 1 qubit or something like that. Because you kind of start thinking, hey, how much information can I really encode in 1 qubit that I can then fully recover, right? With encoding with using like partial phase rotations and stuff like that. That would be interesting to explore. But anyway, so you've got that in here, and then so the way that the other qubit is encoded is by basically messing up with a parity. I think that's the right way to put it. So you've got so if you pay attention, let me just see if I can just zoom in this table and see how the encoding here is happening. If this is gonna allow me to, yeah. So that's awful. I really gotta, the one in here. No. Damn it. I hate this. I think I gotta zoom out, which I can't do right now. Zoom, zoom, zoom. Where do I have the painting tools? I'm just gonna refresh that. Oh my god, that's really messed up. That's really messed up. So I'm just gonna start again. Good. So we're now here exactly. So I just wanted to zoom this in, and you're gonna have to pay close attention now, because I cannot use the drawing tools. I'm really well prepared as usual. But so if we take a look at that bit of information, the one that's the leftmost, right? whenever it's 0, you see that the sign is a plus. Whenever it's 1, you see that the sign is a minus. So that's how you are encoding it in the in the resulting state. And here, whenever it's 0, you see that the qubits are always agreeing, and when it's 1, the qubits are always disagreeing. And you get to that by applying a control knot, because if that's your starting state, and you apply a control knot, a knot, right? If you apply a knot to the qubit on the left side, that's going to turn into 1, and that's going to turn into 0. So you're going to end up with these. So that's how you're using this kind of 2 dimensions to encode information. I think that's the gist of it. And I don't think that should be so complicated to put in these, to explain that a little bit more, because that's not so obvious. I mean, you got to think through this. Maybe that should be posted as an exercise for the reader. I mean, why not? I think it's extremely helpful to put someone through that thought process. That's how it works. That's how it's. So you're basically. Let's move that forward again. So what you're doing is, now, if you can see, the amplitudes have changed from 0 0 to 1 1 to like 0 1 1 0, because this is a 1. If this is a 0, they stay the same. So that's how you encode that information. And so yeah, and so in order to undo this information, in order to read out this information, you apply a control knot right here. So it's a bit stretched to say this is sort of unentangling. That's a bit stretched, I'd say. But you do a control knot. Yeah, that control knot is going to check for party, actually. If you do a control knot in here, if you do a control knot, right? Wait a second. So if you do a control knot, you do control knot, and then you want to read that in here. Can you do that? Can I just transfer that bit of information without the other bit of information? The same we did like some minutes ago, but let's say we don't care about this qubit, and so we don't care about the Hadamard in here. So we're just caring about these. 1 0 seems to work. Why? Because here we've got 0 0 1 1. So when I apply a control knot, I'm basically zero 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 one. So I'm basically removing. It's interesting. It seems like so if this is a 1, it goes all the other way around, so it ends up in here. So you must then, it's kind of getting rid of the other possibility by just kind of checking party. Is it a parity check? It seems like. So if these are your 4 possible states and you're doing a control knot, basically you're going to turn, and now we're taking a look at the Q beat on the classical beat on the right side. And so if I apply a control knot, it's always going to be 0 0 0 1, so we are going to leave this one being 0. And if I apply a control knot here, yeah, it's always going to be 1 1 1 0. Interesting. Yeah. it's still a bit. I'm still not so sure how would you come up with that particular action in here. But it must have to do with party. If they always agree, and if they always agree and you're doing a control knot, now they're not going to agree. But still, you're relying on the fact that this is always going to measure 1 or 0. So that's the bit that I'm like, you can see, you see how the encoding is happening in the 2 different dimensions, but it's still hard to reason absolutely every single step, and why is that step needed in there. How would you, like, you know, that's what you got, like, so you've encoded these 1, you've applied the X gate in here, and you couldn't, I think you just cannot do that without entanglement, right? If I put a 0, no, you're not going to be able to do that without entanglement. That entanglement is needed. There's an overall question here. Both algorithms really rely on entanglement, but it's not obvious how that entanglement helps. And I really haven't figured that out yet, and I really want to figure it out. So, it helps here. It helps because the entanglement allows you to move from agreeing, always agreeing, towards like not agreeing, kind of. So it allows you to move between those 2 states, two different kind of situations. 0, 1, 1, 0. It's not only that they are not agreeing. Yeah, they're always mirrored, right? So exactly, they're not agreeing. So if you do a control knot in here, I'm running out of ideas on how to reason about this. Because we are now what? So this is these 0. The 1 flips it like that into that other state, which is not the plus. It's not the plus state. Not the plus. Sorry, it's not the bell state. As in, like, I think they all have names. It's like the GHZ or something like that, and then they have like GHZ0 or sub 0, sub 1, sub 2, sub 3. I think there are the 4 different cases. So, and now if you apply a control knot, that's effectively, yeah, I mean, I understand. Yeah, maybe there's nothing there to understand more than that, than just, you know, playing with the trial and error style. But that's how you're, or maybe you're unentangling them. It doesn't feel the right way. Anyway, so we've got to the point. So how much time we have left? Okay, so like about 15 minutes. So we've basically taken a look at these 2. So I'm going to use this 15 minutes maybe just to kind of give a bit of feedback based on my current feeling right now. So we've taken a look at 2 algorithms which seem to be fairly simple. I guess once we get into stuff like Grover's algorithm, quantum counting, didn't know that. Okay, Bernstein, Simon's algorithm, I think those are a bit more complicated to understand. So it definitely doesn't help, I think, the reader that there's no kind of walkthrough. There's no kind of walkthrough the actual circuits, or at least there's an explicit action to involve the reader into try to walk through the algorithm themselves. I think just making that, giving the reader the tools to be able to do that is critical. So the book just jumps into those algorithms without really having explained entanglement. Really, let me check. No, I don't think so. I mean, there's no starting gate separate universality by basic circuit identities. Maybe states for many qubits. Maybe because I skipped some of those things. Is there anything here about entanglement? Tensor product. Okay, entangled states. There is indeed something. Okay. Okay. So what is it? Was it here? Using the tensor product, we can construct matrices such as XX, ZZ, ZX, and so on. The expectation values of these also represent probabilities. The ZZ refers to the fact that these probabilities describe outcomes when a Z measurement is made on both qubits. A quantity such as reflects similar probabilities for different choices of measurements on the qubits. The 0 and the 1 refer to whether there are an even for 0 or odd for 1 number of 1 outcomes in the output. So PZZ sub 0 is the probability that the result is either 0, 0 or 1, 1. Okay, so that's like parity. The parity, okay. So these multi-qubit Pauli operators can be used to analyze a new kind of state that cannot be described as a simple tensor product of two independent qubit states. For example, okay, so I'll take my word back. I mean, there is some sense of explanation of the entanglement. This represents a quantum form of correlated state known as entangled state. The correlations can be easily seen from the fact that only the 0, 0 and 1, 1 outcomes are possible when making the Z measurements of both qubits, and so the outcomes of these measurements will always agree. This can only be seen from the fact that blah blah blah. These aren't the only correlations in this state. If you use X measurements, you'd find that the results still always agree. For Y measurements, they always disagree. So we find that this equals 1, this equals minus 1. There are a lot of correlations in this little state. For more qubits, we can get even larger multi-qubit Pauli operators. In this case, the probabilities such as are understood in the same way as for the qubits. They reflect the cases where the total output bit string consists of an even or an odd number of ones. The generation of complex entangled states is necessary part for gaining a quantum advantage. The use of large vectors and multi-qubit correlation functions is therefore important if we want to mathematically analyze what our qubits are doing. Yeah, but it still feels a bit shallow. That part about my point is, it introduces the concept, but there's no some hands-on playing with it. I mean, I don't know really what you could do with it, but I think that separation of you've got the theory here and then you've got the algorithms there, kind of makes it a bit tough for the reader. Yeah. So. Basically. So I think that's my biggest, I would say, point of feedback. And the fact that these here, they don't have a walkthrough. I think they're not that complicated, but I also have to say I've been able to roughly walk through those things because I've done them before. And I spent quite some time trying to walk through those without a lot of the mathematical background that is introduced in here. Maybe that would make the experience a bit better, basically. And I don't think I have much more time to come back to what I wanted to come back in here. What I was doing here, I forgot. So I shouldn't have gotten the teleportation. I should have stayed in here, as you can see. So we're talking about. So what are the open questions? I should dig more into entanglement. I definitely should dig more into entanglement. That's something that I'm kind of missing. Yeah, I'm kind of missing a little bit. So you've got here. I was trying to interpret that whole thing, the whole circuit, as in entangling the amplitude somehow. So it is, to some extent, you're entangling the X dimension, the Z dimension. Sorry, the Z. Yeah, I guess so. But also the X1 for the phases, if that's how you would name it. Because here it seems like the amplitudes are kept the same. It seems like, because yeah, if I pause select on 1, if I pause select here on 1, I basically get these amplitudes back. If I pause select in 0, yeah, but that's too much of a stretch right now. I think my brain needs a rest. Okay, so I haven't really been able to figure out exactly a neat walkthrough. If you take a look at the amplitudes, you see how it works. I just don't. It feels like it's not enough for me, and it feels that's the same that happens with a mathematical explanation, right? It's like you do see that the thing works, you do see what actions you're taking, you do see that happening, but it lacks, to me, it lacks a bit the kind of like the intuition part of it. It doesn't feel intuitive. It feels like you're just playing, mathematically, which I guess is the point of the maths. It's like you don't need to rely on your intuition because you've got the mathematical tools to just, play through the thing. So I'm not saying math is bad. I'm saying math is good, but it feels like it's removing a bit that kind of intuition part of the whole process. And that's something that happened with Gödel's algorithm a lot. But we'll get there at some point. In the next session, I'll try to cover the Deutsch-Jozsa and the Bernstein-Vazirani algorithms. Let's see if that's going to be possible. Then we will do Simon's algorithm. Probably will be one session in and of itself, I think, because I want to do the QFT and quantum phase estimation together. And then Grover algorithm is going to be another session separate, maybe with quantum counting, I think. I don't know. We'll see. But I'm not going to be like doing 2 per session. We will see. I think Simon's. I don't remember. I did Simon's algorithm a while ago, and I just forgot about it. So what was that even? Okay. Doesn't seem extremely. Yeah. So here there's some mathematical walk through the different states, and that's what I'm saying. It's kind of like it's gonna help you understand that, but it's not. It's at least not intuitive for me. Anyway. So I think I'm gonna leave it here. It's like we'd still have some time, but unless anyone who's currently watching has any particular question, then I'll leave it here. I just feel like I run out of brain juice to, especially I shouldn't have switched to Superdense coding maybe without, but it just feels it's open-ended exploration, and that's just not productive for my brain either right now. But I think it's been fun to try to break down these things, play with the circuits a little bit. It's definitely interesting stuff. And this quantum entanglement thingy, it just feels like I really need to explore that a little bit more, the entanglement part of it. Cool. So I hope you've had fun. Let me quickly check in Slack if there's been. I mean, that session is not supposed to be oriented to feedback right away. But if you've got any questions, feedbacks, any things that you've spotted in there, just put them in the Qiskit Slack textbook reading group channel. For me, it was a couple of things that confused me here with the Superdense coding and the order of the operations and whatnot. But it's not that relevant. The biggest feedback point is kind of I'm missing a bit that intuition part of it, but I guess that's why my channel is called Quantum Intuition, because that's probably it's maybe my thing. I guess not everyone needs that or is seeking that. So anyway, I'm gonna end the stream here. I'm happy to see there's been a lot of playbacks. There's been really I can see here like average watch time 10 minutes. That's really big. It's growing. It's growing. If you compare it to the other sessions, so it makes me really happy. And yeah, stay tuned for more. And I guess we'll see each other in the next session. Sam is doing another session for personal study later today, so join that as well. And yeah, have a good day.